So this talk is going to be NOVA, which is a high-speed recursive zero-knowledge argument. This is joint work with my former MSR interns Abhiram and Yana. This work has been implemented. It was described at Crypto a few months ago. So I'm going to start with a very high-level overview of what NOVA is. So in a nutshell, NOVA is a recursive proof system that provides state-of-the-art efficiency. It has a fast prover. In particular, the prover time is dominated by two multi-exponential size proportional to the size of the circuit that you're proving. In concrete terms, this is like a few microseconds per constraint that you want to prove. And this is like because the number of multi-exponentiations that NOVA performs is so small, it's one to several orders of magnitude faster than existing proof systems. No also has a low recursion overhead. In fact, it's the lowest. I'll come back to what this means later in the talk. At a very high level, the cost of verifying a NOVA proof inside a circuit is very small. It's about 10,000 R1CS gates. No also produces small proofs. In particular, it only produces a logarithmic number of group elements. In practice, this is about 8 kilobytes in the current implementation. Nova achieves all these new properties with new techniques, and it also leverages some existing best-in-class techniques, as I'll describe later in the talk. So the new technique that Nova introduces is what we call a folding scheme, and it also leverages existing techniques like the linear time sum check protocol. There is a high quality implementation of Nova, as I mentioned earlier. It's open source. It's about 7,000 lines of Rust. It's generic over the elliptic curves. Today it uses pasta curves, but one can plug other curves like BN254. It's parallelized on CPUs using Rayon. It also, for doing multi-scalar multiplications over the pasta curves, it uses pasta MSM from supranational. That library can also leverage GPUs. So in the rest of this talk, I'm going to provide a brief description of how Nova works. I think there is an issue with the clicker. Okay, so at a very high level, Nova's goal is to build these practical ZK snarks for recursive computations. What I mean by this is we have a computation that's represented in multiple steps, and at each step, it takes as input some non-deterministic witness from the prover, which I've denoted here with W's, and it also takes as input some output from the prior step of the computation. So the goal is for the prover to prove that this recursive computation is executed some number of times with some well-known public input and well-known public output. And this actually captures many real-world applications. For example, in the case of a verifiable delay function, this f simply represents some number of iterations of a delay function like minroot. And in the case of a rollup, this F represents a one or more steps of a VM, for example, the EVM or Lurk VM or the Cairo VM. Or it can also represent some CPU emulator like RISC-V. So if we take a look at this recursive computation, one naive approach to prove such recursive computation is to roll this n iterations of F into a single circuit. And then we can just take a state-of-the-art snark to produce a proof. But there are many downsides associated with this approach. One of them is that the prover would have to use memory proportional to the number of iterations of f. And the proof is also not incrementally updatable because once I produce a proof for some number of iterations, I cannot update it to account for more iterations of the same function. And depending on the snark, the verifier's time to verify such a proof might also depend on the number of iterations that were executed. So to address this problem, Valiant proposed something called incrementally verifiable computation. And in this setting, what happens is instead of actually proving F, it proves an augmented circuit, which I have denoted on this slide by F prime. What this augmented circuit does is it composes F with some verifier circuit. I'll explain what this verifier circuit is going to do. But at each step, it's the prover is producing a proof of F prime, and it takes as input the non-deterministic witness as before. It also takes output from the previous step, but one new thing in this picture is a proof of the prior step. So at each step, the prover produces a proof and feeds it to the next step, and the prover incrementally updates this proof as it goes. So as a result, the final proof attests to the correct execution of the entire recursive computation. This approach was implemented by BCTV about a decade ago, and there are several downsides with their implementations. For example, that approach requires expensive cycles of elliptic curves. In particular, those cycles of elliptic curves must support pairings. And the particular snark that they used also required a per F trusted setup. Today, there are snarks without trusted setup, so-called transparent snarks, and we could re-implement this BCTV14 with one of those transparent snarks. But the existing transparent snarks have much larger verifier circuit, for example, tens of millions of gates. As a result, the prover's work at each step of this recursion has substantial overhead for supporting recursion. So, to address this problem, Halo provided an innovative approach where it follows the same blueprint as what I described on the previous slide. But instead of the verifier circuit actually verifying a snark, it partially verifies the snark, deferring some of the most expensive steps in the verification of a snark. This reduces the size of the verifier circuit, but it still has some downsides. For example, the prover must still produce a snark. For example, in the case of Halo 2, it has to produce a snark using Plonk, which can be concretely expensive. The verifier circuit is also still substantially large. For example, a million gates. This also means there is a large recursion threshold, recursion overhead associated with this approach. What Nova does is one way to think about what Nova does can be to take the approach that I just described fireworks, except that the proof here is a commitment to a witness rather than a snark. So it does not produce any snarks, it simply commits to the witness. As a result, the prover's work is, for example, several orders of magnitude cheaper than other proof systems that might have to do a lot of polynomial commitments and prove their evaluations. The verifier circuit simply takes a linear combination of those commitments. So it's not verifying any snarks. As a result, it gets us to the lowest recursion threshold that in the literature. For example, in our implementation, this is only the verifier circuit is about 10,000 gates. There is one downside to this approach compared to the prior approaches that I described, which is that the recursive proofs are not succinct. In particular, the recursive proofs are a linear number of group elements, and it's linear in the size of the circuit at each step. But we address this downside by actually invoking a snark that compresses the proof down to a logarithmic number of group elements. So one point that I want to make here is that this the proof system that we invoke to compress proofs is based on linear time sum check. So it does not actually add much to the proving overhead, especially if you perform a large recursive computation and then invoke this infrequently. So the way we achieve these properties is by using what we refer to as a folding scheme. So at a very high level, this folding scheme is a protocol between two entities. One is a prover and a verifier. The prover has two NP instances, U1 and U2, and it also has the purported witnesses to these instances, W1, W2, and the verifier simply has instances. You can think of these instances as circuit satisfiability instances. So the goal of a folding scheme is, with some hint from the prover, the verifier wants to output a single instance, a single circuit satisfiability instance, such that this output instance is satisfiable only if the original two instances were both satisfiable. And another requirement for a folding scheme is that verifying this U is concretely cheaper than verifying both of the original instances individually using their purported witnesses. This is inspired by inner product arguments, where the prover and the verifier typically combine two inner product instances into a single instance. Whereas in our context, we are trying to fold two general NP instances. So, if there are snarks that are general purpose, they actually trivially imply a folding scheme for NP. Here how it goes. So the int can just be a snark that U1 is satisfiable, and then the verifier verifies that hint and then sets the folded instance to be the other one. This actually works, but our goal is to actually provide a folding scheme for general class of languages without actually using snarks or even arguments of knowledge. And this is one of the key theoretical contributions of Nova. And to actually explain how Nova's folding scheme works, I like to take a small detour to introduce R1CS. So R1CS is a characterization of NP, and it also generalizes arithmetic circuit satisfiability. So here there are three M cross M matrices ABC, and there is some public input X. The goal of the prover is to prove that there exists some witness W such that this operations on the matrix hold. AZ, a circ BZ equals CZ, and where the circ is the entry-wise multiplication of the vectors, and the Z is the concatenation of the witness with the public input and the constant one. So in this problem, the witness is W, as I mentioned, and the instance is these three ABC matrices along with a commitment to W and the public input. So one thing I want to point out here is that in standard R1CS, typically don't have the instance to hold a commitment to the witness, but uh, I'm going to ignore this issue for now. Also, suppose that these commitments that we put inside the instance are linearly homomorphic. For example, think of Pedersen commitments, where you can take two commitments and add them to get a commitment to the addition of the underlying data. So to illustrate our eventual folding scheme for R1CS, I'm going to start with a failed attempt, one that will not work, just to illustrate the difficulties. Suppose we have the setup as before, where the prover holds the two purported witnesses, W1, W2, and suppose the verifier holds the two instances, which are commitments to the witness and the public inputs. And suppose the verifier just picks a random R and it sends it to the prover. And then here is suppose this is how we compute a folded instance, where we simply take a random linear combination of the two commitments. Because these commitments are additively homomorphic, they can be added with this random scaling. And suppose we also do the same for the public IO. And on the prover also takes a random linear combination of the witnesses. But unfortunately, this is not going to work, because for many, there exists R, and in fact, for many R's, the folded instance is not satisfiable, even if the original instances are satisfiable. What this means is this solution does not even provide completeness, let alone soundness or other properties that we need. So, let's examine why this actually happens. If we take the LHS of the folded instance, so which expands to these linear combinations, and if we distribute this and expand this out, we have some extra terms which are the multiplied by R, and the second instance is also multiplied by R square. Whereas if we take the right hand side, it's simply a linear combination. So it's very clear that for many values of R, the LHS would not be equal to the RHS. So to address this problem, what we do is we introduce what we call relaxed R1CS, which is a variant of R1CS that allows us to perform folding without those cross terms. In particular, what we do is we have the setup as before, the ABC matrices, which are M cross M, but we change the satisfiability check to include extra terms. There is a scalar U and there is also a vector E. And we also change the definition of Z to include U instead of the constant one. So the instance consists of commitments to both the witness vector, the slack vector, and this new scalar that we introduced, which is U, and also the public input. One thing I want to point out here is that this relaxed R1CS and R1CS both are characterizations of NP. In fact, you can try if there is any R1CS instance, it can be converted to relaxed R1CS instance and vice versa. Just to illustrate this point, for example, if you are given an R1CS instance, you can simply set U to 1 and the slack vector e to 0, and this gives you a relaxed R1CS instance. And there's also a other way around. It's a little bit more involved, but it's possible. So now we are given this relaxed R1CS instance. I'm going to show you how to fold two relaxed R1CS instances. So the setup is as before. The prover has two witnesses and the verifier has the two instances. So unlike before, the prover starts by sending a commitment to the hint, which is a nasty cross term, and I'm going to denote this with T. And then V picks a random R as before and sends it to the prover. V computes a folded instance as I'm going to show you next. So it just takes a random linear combination of the witnesses for computing E. The folded E takes the original two E1 and E2, but it also uses the commitment that was sent by the prover T, which I denoted with T. And for the other two scalars, like the public input and the U, it just takes a random linear combination. And the prover does the same for the original plain text contents of both W and E. And in the paper, we show that this preserves we prove completeness, knowledge soundness, and the zero knowledge property for the folding scheme. The one intuition is that by introducing this extra term E, it absorbs all of the cross terms that were present in the failed attempt, and E also absorbs the multiplicative factors. So the result is that the folded instance has the same structure as the original instances. So this allows us to get both completeness, and we also prove other properties in the paper. So once we have a folding scheme, I'm going to describe how we get incrementally verifiable computation from this. And this is going to be a high-level sketch. So the setting is as before. At each step, the prover is going to prove the correct execution of this F augmented with the verifier circuit. And in NOVA, we represent this F prime as R1CS. And then we have at each step, the prover produce this so-called proof, but it's simply commitments to the witness and the cross term T. And this W is the witness for this particular execution of F prime. And then the verifier circuit maintains verifier circuit has some state, which is a what we call a running relaxed R1CS instance. And all it's going to do is it takes this pi I that has two commitments, and it folds those incoming commitments into the running instance. And so what this means is that the verifier circuit is just performing some scalar multiplications inside the circuit. So after running this protocol for n iterations, the prover has one running instance and one running witness. So to prove this entire recursive computation, the prover can just send both of those to the verifier, who can ensure that the initial input is what is expected, and it can take the final output, and it can also just verify that the witness satisfies the instance. But there is one problem with the naive solution, as I alluded to earlier, which is that these recursive proofs are of size linear in the size of the circuit that we executed at each step. Um, and this has two issues. One is obviously the proofs are large, both asymptotically and also concretely. Uh, and the second problem is that these proofs are not zero knowledge. So they don't hide anything about the computation that was executed. So in principle, one can take any ZK snark, and they can recursively prove the knowledge of this valid IVC proof. It provides both succinctness and zero knowledge. But one problem with this theoretical solution is this can actually be very expensive. One reason is that the in the solution the prover must prove it knows W, such that W is a commitment to a public value that was part of the instance, and it also must do prove other things. And all of this requires a ton of non-native arithmetic, which can be expensive. So what Nova does is it interprets these commitments that we were using earlier, the Pedersen commitments, as commitments to polynomials. In particular, it treats them as polynomial commitments to multilinear polynomials. And once we do this, we can invoke Spartan. In fact, a small modification to Spartan to directly prove that those polynomial commitments satisfies the relaxed RNCs. And it also produces a snark, and the proof sizes immediately go down from linear in the size of the circuit to a logarithmic number of group elements. And Spartan is, I didn't go into the details of how Spartan works, but it's based on linear time sum checks. So it's, as I alluded to earlier, producing a snark is inexpensive, especially if we do this after a large recursive computation. So to summarize, ANOVA is a proof system with a fast prover. It does not require any trusted setup. It produces small proofs. It has new techniques such as folding schemes. It also leverages linear time sum checks to get proof compression. This is fully implemented, available on GitHub. There is also a Rust crate with documentation. There is some stream of ongoing work to further improve the performance and also expand the capabilities of this proof system. One takeaway that I want to mention here is that Nova offers a new substrate for building proof based, trustless services with many advantages over other proof systems. And with that, I can take any questions. So when I say trusted setup, I was referring to something very specific. What I meant is you don't need this multi-party ceremonies that you may have heard of for other ZK snarks, where all of these parties need to produce this structured reference string. The Nova still requires a setup, but it's not trusted. So anyone can just create a sample. Everyone needs to agree on the group generators that we are going to use to verify the proof. So there is still a notion of a verification key, and there is also a part of the verification key that embeds these ABC matrices that you are going to prove. So you still have some key material that's going to be useful for verifying the proofs,
Hmm. So,
but it is not trusted. Like, you don't need a multi-party ceremony to create that material.
yeah, got it. Thank you.
If you look at the left-hand side, that it expands into AZ1 circ BZ1 plus R square, this AZ2 BZ2. And then there is also the third term, which is multiplied by R, and that's a cross term. But if you look at the RHS, CZ1 corresponds to the first term in the LHS, and then there is R times CZ2. So AZ2 is BZ2, so that's fine. But the RHS has no third term. That cross term is not present, and there is also R square, whereas in the RHS it's simply R. So that's why the it does not even satisfy completeness. Even if the original instances were satisfiable, the folded instance may not be satisfiable, which is not desirable. Does that make sense?
Is it that the E that you like the linearity that you introduce allows you to always cancel that R squared term and kind of get rid of the problem? Like, is that what the relaxation does?
So we have two modifications. One is the scalar u, and then the slack vector e. And the slack vector e captures all of these extra cross terms, and u takes all the like this avoids. If you look at the e, it multiplies r with r and t, and then r square with e2. So it definitely, you can just write this out on a paper, and it can see that this it satisfies completeness. Knowledge soundness is a little more tricky. It's in the paper, but it's very easy to see completeness. There is definitely a low level interface. In particular, it supports bell person. Sorry, I did not mention in one of my slides. It supports bell person to express your constraint. So you could specify the step circuit directly using bell person constraint system or any compiler that allows you to write these. Lurk is definitely, I guess, the one of them that automatically hides all of this from the user. But we have implemented VDF directly using this bell person interface.